Today on Flipping Science, we're looking at atomic structure. So the understanding we're going to cover today is that all material consists of atoms, and atoms are commonly modelled as consisting of electrons orbiting a nucleus containing protons and neutrons. So what are atoms? Atoms make up everything. All the matter around you is made up of atoms, but they're quite small. So because they're quite small, it took quite a while to figure out that they existed at all, because you can't see them easily. Their size is very small, like I said, ranging from about 30 to 300 picometers. So that's 30 to 300 trillionths of a meter. So again, very, very small. We can't, as humans, we can't really even picture a trillionth in our head. This periodic table here shows you the size of the radius in picometers for elements that we have information for that, and that's plus minus 5 picometers. So you can see relatively small on this side if we're looking at the non-metals, and larger over here with the metals, and then the further down you go, the bigger the atoms are. This is a scanning electron micrograph of gold. So this is gold foil, and you can see these individual dots there, they're each individual atoms of gold. So how do we get to the idea of atoms and what makes them up? It's a long story, I'm going to cut a lot of it short. This guy down here, so here's a contemporary painting of him, nobody really knows what he looked like. His name was Democritus, and he came up with the idea that if you cut something in half, for example, cheese, he liked cheese. If you cut a piece of cheese in half, then it's still cheese. If you cut those halves in halves, then it's still cheese. And he said eventually you get to a point where what you cut in half isn't cheese anymore. So things must be made up of these tiny little bits that make up matter. Give it a few, nearly 1,000, 1,500, 1,800 years, you get to John Dalton over here, and he proposed that matter is made up of clumps of matter that can't be broken down into small stuff. They're both wrong, because we can break up atoms into smaller things, but the idea that everything consists of fundamental tiny particles is kind of shared between them. And then Lavoisier came along and noticed that when reactions happen, you got fixed ratios of products from reactants, or fixed ratios of reactants forming products. Here's Lavoisier down here. This picture has cut out his wife, who did a lot of the work with him, but she gets very little credit. So he knows, for example, that if you burn 2 parts of hydrogen with 1 part of oxygen, you get 2 water parts coming out. So because there's fixed quantities there, that suggests that there must be tiny bits that work in fixed ratios with each other. Now, for a scientific theory to be valid, it should have an explanation of why things are happening, and evidence needs to be provided for it. So it needs to explain the idea and explain why things happen, but also with evidence for why those things happen. So Dalton's idea didn't really go very far because there wasn't enough evidence at the time, but because Lavoisier started producing evidence, people started to take more notice of it. Dalton was quite a scientist. He's also famous for figuring out how colour blindness works. So after a while, people were happy that things were made up of atoms, but people wanted to know how the atoms were arranged themselves. And advances in technology allowed people like J.J. Thomson down here to figure out that there were these things that carried a negative charge that existed in atoms, so the electrons. You figured that out by making these discharge tubes. You heat up a metal, the electrons fly out, and you can attract the electrons if you have a positive charge. So because the electrons are attracted to the positive charge, that tells you that they're negatively charged themselves. His work led to the plum pudding model, which is this model over here, which is where the atoms are kind of balls, and inside those balls you have positive and negative charges kind of randomly distributed around it. This was around for a while, but then Ernest Rutherford came along and found that atoms were mostly made of empty space. So Rutherford down here, along with Geiger and Marsden down here, mainly Rutherford gets the credit for this. They did this experiment called the gold foil experiment. So they fired alpha particles from a radioactive source at a strip of gold foil, and around it they had some photographic film. Alpha particles have a positive charge, so if they hit something positive, they're going to change direction. What happened was they found that most particles flew straight through, a small amount of them were deflected, and some even bounced back towards the radioactive source. So these results suggested a few things to Rutherford. Since most of the particles were just flying straight through the gold foil, that means that the atom has to be mostly empty space. Very few of the particles were being deflected. Particles that were deflected, they were being deflected by something that's pretty heavy and has a pretty big charge. So the alpha particle with a positive charge is repelled by other things with positive charges. The alpha particle comes in, moves past the electrons, gets close to the nucleus, is repelled, and then bounces off. And that explains why they were being deviated in the way that they were. But it was very surprising because the amount of deviation you got was quite big. So Rutherford said it's like firing a 15-inch cannonball. So 15 inches cannonball, about, get my hands right, about yay big, depending on your scale, at tissue paper and having it fly back towards you. So that's kind of the relative size of these things that are being fired at each other. So with Rutherford's discoveries, the plum pudding model went out and we got to eventually this thing called the Bohr model, which we'll talk about a bit later on. There's a small positive nucleus in the middle of the atom and the electrons with negative charge are flying around the outside. This took a little, this was proven in a different way a bit later on, and like I said, we'll look at that later on. It messes with my head and it should mess with your heads. Most 99.999% of the space inside an atom is empty space. That means you are mostly empty space. Everything is mostly empty space, even when it is composed of matter. Here's an analogy down here. If an atom is a 14-story building, then a nucleus is about the size of a grain of salt. So yes, the relative sizes of these things are baffling. So from the discoveries of those scientists, along with a lot of work of other scientists, we get to the subatomic particles and how they're arranged in atoms. So we talked about protons, neutrons, and electrons. So the protons, they have a positive charge and they're found in the nucleus, which is the center of an atom. The neutrons, they're also found in the nucleus, but they have no charge. And then the electrons, they're not in the nucleus, they're dotted around, flying around at really high speeds in these structures called shells. They're not really structures, they're just energy levels where the electrons can exist. So they fly around in space. Now, the problem with any of these pictures down here is the scale. Like we said before, and if an atom is a 14-story building, then the nucleus is a grain of salt. That doesn't really work with these scales of pictures, but these are just models to keep in your head. So let's talk about protons. So here I have a model of lithium. I'll rotate it that way. We've got some protons and neutrons in the nucleus here. The orange balls here are the protons. So lithium has 3 of them. The number of protons tells you what type of atom you have. So lithium has 3. Down here I've got some pictures of hydrogen. Hydrogen has 1 proton. Helium has 2 protons. And this is part of how the periodic table is arranged. It's arranged in increasing order of atomic number. So as you increase the atomic number up here, you're increasing the number of protons in the nucleus. And that has very important chemical effects. Neutrons took a little while to discover because they don't have a charge, they don't do much. So in my little model of lithium here, the yellow balls, they're the neutrons. So neutrons are very important because they stop the nucleus of an atom from exploding. They hold protons together. Protons have a positive charge, so if you put 2 positive charges together, they try and get away from each other. The neutrons hold them together. The bigger the atom, the more neutrons you need, and that's where this curve comes down here. So here we have a ratio of 1 to 1. As you get more and more protons, so we're increasing the number of protons down here, you have to increase the number of neutrons above that 1 to 1 ratio. So why is this important? If you don't have enough neutrons holding the protons together, the atom does explode, and that's what radioactivity is. So here we have a few different types of radioactivity. So we've got beta and alpha. You get alpha emission when you have too many protons for the neutrons, and if you have too many neutrons for the protons, you get beta emission. So these are the 2 different types of radioactivity. If you're interested in this stuff, it's a good idea to do physics, because they do nuclear physics in physics. We don't really do too much of it in chemistry. The electrons are, for chemistry, probably the most important thing. Chemistry is all about reactions and how atoms interact with each other, and that's all down to what the electrons do. The number of electrons is determined by the number of protons, and where the electrons are is determined by how many shells of electrons that you have. What can happen is electrons can be exchanged between atoms like this. This is an ionic reaction where one atom gives an electron to another one. Or they can be shared between atoms. So this is covalent bonding down here. So we're sharing electrons between atoms and that sticks them together. There's also metallic bonding, which we're also going to look at later on. So chemistry is really about where the electrons are and what the electrons are doing. That's what chemistry is based on. So what makes one atom different from another atom? It all comes down to the number of protons in the nucleus. Those number of protons determine the number of electrons, and how many electrons you have determine how things react chemically. Number of protons also in part determines how many neutrons you have in order to hold the atom together and stop it from decaying radioactively. So they all kind of interact with each other. So today on Flipping Science, we looked at the structure of atoms. That's it for Flipping Science today. See ya.